Hey everyone. So last time we talked about the complex numbers, which were numbers of the form a plus bi, where I had the special property that it's squared to -1. And we said we could draw them in a nice way. We could draw them on an axis, where we put the real part, that is the a part, across the x-axis, and the b part, the imaginary part, on the y-axis. So we might have drawn something like this to represent 2 plus 2i. Now this diagram has a special name. It's called the Argand diagram. And it gives us an indication that there might be a better way, or at least a different way, to represent a complex number. So we can describe this arrow in the way we are at the moment, which is by saying it's 2 across and 2 up. But we could also describe it in a different way. We could describe it with this angle here, which I'm going to call t, and a number r, which tells us how long the arrow is. So we can use a bit of high school trigonometry to tell us that a is r cosine t, and b is r sine t, because they are respectively the horizontal bits here and the vertical bits here. Now, these r and t have special names. R is called the modulus, and t is called the argument. But really, you can think of r as being the length of an arrow, and t as being the angle the arrow makes to the positive x-axis. So, using this, we can write a plus bi as r cosine t plus r sine t times number I, which, for convenience, will often pull the r outside, so we can write it like this. So, to give an example, let's imagine we're told we have some arrow that makes an angle of 45 degrees and has a length 2. Then we know that cosine of 45 degrees is the same as the sine of 45 degrees, which is the square root of 2 over 2. So that means that a is 2 times the square root of 2 over 2, just the square root of 2, and b, we get exactly the same thing. So we see that this number represented by the modulus 2 and the argument 45 degrees is actually nothing more than the square root of 2 plus the square root of 2 times I. Now let's look at how we go the other way. So how do we find the modulus and the argument of a given complex number? Well, to find the modulus, we'll denote it with bars on either side of the number, and this is just written as the square root of a squared plus b squared, which is in fact the same as the number z multiplied by its complex conjugate that we learned about last time. The argument that we're going to write as arg z also has a simple formula, and it's just the inverse tan of b over a. So let's do an example. Let's take the square root of 3 plus I, then its modulus is going to be the square root of the square root of 3 squared, which is 3, and plus 1 squared, which is just 1. So this is going to be the square root of 4, which is 2. Then, if we work out the argument, well, the argument of 3 plus I, or square root of 3 plus I even, is going to be the inverse tan of 1 over root 3, which is just 30 degrees. So that tells us we can represent this complex number with an arrow, and the arrow is going to make an angle of 30 degrees and have length 2. So, the important thing we now should talk about is what happens is, can I have a negative argument? And the answer is yes. So far, we have thought about the argument as being the angle we make to the positive x-axis. So we go around this way. But equally, we could maybe have gone round the other way. So all we do is we say when we go round clockwise, we use a negative argument. So we say this might be minus 45 degrees, and this one might be minus 315 degrees. Sorry, positive 315 degrees. Either way, they represent the same number, because we either go around anti-clockwise, 315 degrees, or we go around clockwise, 45 degrees. And finally, the last thing I want to talk about is Euler's formula. This is a really marvelous formula in mathematics that tells you that e to the it can be written as the cosine of t plus I sine t. But we've already seen we can write any complex number as r cosine t times I plus I sine t. So we can use this formula to say this is just r e to the I t. Now this turns out to be a really helpful way to write a complex number, and we're going to use it all the time in quantum mechanics. And to see why, let's see how multiplying two numbers in this form works. Well, this is just multiplying numbers, so we can write this as r1, r2 times e to the I t1, e to the I t2. But when you multiply exponentials, you can add the numbers up here. So this is just r1, r2 times e to the I t1 plus t2. So all we had to do was multiply together the moduli and add together the arguments. It also makes it actually really easy to find a complex conjugate, because the complex conjugate of r e to the it is just r e to the minus it. And this is all we need to know for now. So thank you, and I will see you in the next one.